Okay, so started. Acha, so I had ended last class with a question to you. When we actually see colors of any material, what does that mean? Or like, what is the physics behind that? Given that we sort of, can you see the whiteboard? Can you see the whiteboard?
Yes.
Yes, sir.
Okay, yeah. So given that we have this kind of, so what we have done till now, of course, is basically find out how these optical constants essentially are the dielectric constant of the material. So we are dealing, again, just a very, very brief recap. So we are dealing with these dielectric materials essentially, which mean that they have some kind of bound electrons which interact with light and give rise to refractive index of the material. So refractive index we have seen consists of the real part and the imaginary part. And remember, it is the difference of refractive index between two mediums, between two media, that is, which give rise to reflectance and transmittance properties of light as it passes between one media and the other, right? And what we have seen, of course, in the first thing that we studied in this course, that is Snell's reflection coefficients and transmission coefficients and all that, we did not consider absorption, we did not consider any frequency response. The only thing we considered was polarization. Okay, so here polarization of light. So now we have actually considered absorptance as a very important phenomena, so we have seen that you have the refractive index of light has both the real and an imaginary part, and the real part is associated with the progression of the wave, while the imaginary part basically deals with absorption in the medium. So this is how both of them behave as a function of frequency of the input light. So you have this is the real part, which is for the progression of light, and this is the imaginary part which gives rise to absorption, right? Okay, and my question to you was, what finally, how would you describe the physics of colors, or how does a material color of a dielectric material? And this is a very large scope of material. I mean, lot of things around us essentially transmit light. What I'm saying is that these are not substances which just absorb light completely. Will be absorbance, and there will also be transmittance. Things like that. Metals are a different class of materials. Dielectric materials are representing much of the stuff that we see around us. Okay, so what are the thoughts? So what we have learned is the refractive index has real and imaginary components. This is responsible for progression of EM wave through the medium, I should say in a medium, while this gives you absorption. Okay. So now, given that you know this, how can you explain why an object looks red or blue or green or anything? What do you think happens? What do you think happens? Yeah, what?
Certain frequencies are absorbed while the rest is transmitted or reflected. So what we see as the color is the part which is reflected, right? So
Very good. Very good. Yeah, that is very true. So, Acha, another very crucial question that comes here Is the color of a material permanent? Do you understand what I'm saying? I'm saying that it is independent of everything, in the
No, sir,
sense
it
that,
will
uh,
also depend on the like what are the wavelengths contained in the
correct,
incident light. Otherwise,
exactly.
like
That is
yeah.
a very, very, very important concept. Does the class appreciate this? What is the meaning? So, as Chitudip said, basically what happens is when you actually illuminate an object, when you illuminate an object with a range of wavelengths of light, you basically have some colors absorbed, some colors reflected, and what comes to your eyes as reflected color, they may combine with each other to produce the final color of the object. And if you change the incident light, the color will also change. So let me now pose a question. What do you think? So we have seen that at resonance what happens? At resonance, so basically n has dispersion, right? This is what we really learned, right? Which means so basically n omega has interesting properties with uh, properties as a function of omega, right? Now what we saw n1, which is the real part, that is low, so that is like n1 minus 1 is 0 at resonance, and k omega is maximum. Okay, now let me pose this interesting question. What do you think? So this is so very clear, right? At resonance, the absorption is maximum. What will happen to the reflectivity? What does the class think? When the absorption is maximum, suppose I come with a color red light, say, okay, and I have a dye which is also absorbing at red. I mean, which basically has a absorption maxima. So basically, say, suppose you have some cloth which is dyed in red color, okay, and that color has the maximum absorption at some light which is actually incident on it. Suppose the 600 nanometer light I'm incidenting on this cloth, and the dye that is the cloth is smeared with, that has a maximum absorptance at 600. So what do you think will be the reflectivity?
It
So
will.
then will it be, so let me ask you this. It's very interesting. So let me pose the question like this. Suppose you have a plethora of colors, you have a mixture of colors, okay, red, blue, green, yellow, whatever, but you have a dye which is absorbing at red, okay. So what will the color of the material be? Will it, yeah. Did you get the question? I have
Yes.
some white light coming, and I have a dye which is absorbing at red, huh? And what then will the material appear predominantly? Predominantly,
So
what will be the color of the material?
the color that is complementary to red, basically.
So what Anirudh feels is that if the K is maximum at resonance, the reflectivity will be minimum. Is that what you feel?
Sorry, sir. Can you repeat
What I
what?
said was, are you saying that if K is maximum, that is the absorption is maximum at, say, some frequency, suppose as I said, I'm coming with 600 nanometer on a red dye, which means it's going to maximum absorb. Okay, so will the reflectivity at that color be minimal?
No, actually, it need not be necessary
Hmm. What makes you say this?
because reflectivity comes from those Fresnel relations, right?
Okay, so let us calculate the reflectivity. Very good. So reflectivity. What did so again we saw again normal incidence. Huh? I'm not complicating affairs. I'm saying that this is normal incidence, right? So that is what. That is, so suppose n1 and n2. You have n1 minus n2 by n1 plus n2, right? And I suppose I say that let this n1 by n2 be some m, right? In which case this will then become this r. This is like r. This r becomes what? Then r is tell me what it will be.
M
Can I
minus
write
1
this?
upon M plus 1.
Exactly. Very nice. Very nice. Now suppose I say that I like write this m as some, n plus ik. This is I can do that, right? I can. This is some kind of relative thing that I'm writing. There is a real part and an imaginary part, right? Then what does r become? Basically, it will become n minus 1 plus ik. Actually, I should not have written this capital R. Yeah. Should be smaller. So, smaller. I think the reflective intensity should be capital R. Okay. Oh, shit. No, it will be difficult to write. What was this? Okay. N minus 1 plus ik, and this will be n plus 1 plus ik, right? So then what will be your r? Reflectivity is basically r star r, right? So that will be what now? What? This iska complex conjugate se multiply, right? So I will multiply by n plus 1 minus ik upstairs. Oh, na kya hoga? It will be multiplied by r star, right? R star basically mane n minus 1 minus ik by n plus 1 minus ik, right? Correct? Can I write this? Is this fine? What? Right?
Yes.
Silence. This is correct, no?
Yes.
Correct? Abhi moza dekho. So then that this is my reflectivity. Then this is very important result. Let me write this down again. So basically your R is n minus 1 whole square plus k square. This is very crucial as a result. N plus 1 whole square plus k square. Let me nicely decorate it. Right? Now, what happens at resonance?
Sir, I'm not sure whether that expression is correct.
Why?
Because numerator denominator seems fine, but there's something wrong with numerator.
Why?
Because since you're multiplying by the complex conjugate of the denominator, that n plus 1
No,
whole
no, no,
square
no.
plus
I'm
k
saying
square is
complex
fine.
conjugate, everything will become this thing, right? कॉम्प्लेक्स कॉन्जुगेट माने तो ये उल्टा हो
Oh,
जाएगा,
okay.
राइट?
Okay.
उल्टा हो जाएगा ना. Don't confuse. I am not taking. Yeah. This is very important class. I am not taking absolute value. I am multiplying by complex conjugate. Absolute value will be very different. I am multiplying by complex conjugate, right? So then at resonance, k is very large, right? You can say that k is very large. I should not write this. I should basically write. Well, this is maybe, yeah, it's very large, much larger than 1 should be right, or much larger than, yeah, I think we should write much larger than 1. Let us see. It's very large. Okay. So that means, and so by the way, what is n? N minus 1 at 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 resonance. Yeah, N minus 1 at resonance,
Zero.
0.
0, right? And also I can assume that this quantity is much lesser than this quantity, because anyway your N is close to the refractive index of air, when basically like 1, which means that this is like whatever 4. So this, what does it imply? That R is very large. So this is very interesting, right? Right at resonance, you actually have very high reflectivity. This is quite counterintuitive also, right? You feel that the reflectivity is depending on absorb. I mean, if the material has high absorptivity, then it will not, reflect anything. It is not the case. It is not the case. The reflectivity actually is very high. Okay, so that means essentially that this dye which will absorb red at the maximum at like at if you actually irradiate the dye at its resonance wavelength, then it will also reflect most, and it will of course appear red. This is very important, right? So essentially what it translates to is that colors other than the I mean, let's say the resonance color, if I may say so, resonance color are absorbed, and the resonance color color is reflected. So this is very interesting as a concept. So when you basically have very high, the very high sort of absorption coefficient for a certain color, actually the reflectivity, as we understand, by the Fresnel laws, the reflectivity is actually pretty high. Okay, so this is a very interesting interplay of the electromagnetic, the field and the material, and the way we define this thing. That this is, it tells you that the colors so that then you can completely appreciate that if I change the the incident colors, that's very interesting, right? So you will basically be playing with that the absorptivity, and so the reflectivity and the absorptivity, right? So the final net color will completely depend on this ratio for all the different wavelengths that are incident. This is very interesting. So if you just, so therefore, please understand what is the basic takeaway of this. The basic takeaway is that colors essentially, uh, the color of an object is entirely dependent on the wavelength of illumination, right? So please understand this. It is another thing, another, you may say, another feather in the cap of relative concepts. So color is only relative. If you change the incident set of wavelengths, incident in illumination, color will completely appear different. And that is what, for example, this is what drives people who are very much into aesthetics. Okay, so when people try to design lights, so this is now a very emergent field in both advertising, in in the performing arts and all. where people actually, nowadays they design, colors, they design, the dress of performing artists. Everything is designed taking into consideration the net, display, the net sort of, illumination, the what should I say, the net appearance of, the artist or the object which is being viewed. That has to be taken into consideration, not just, if I am sort of, I create some colors to portray certain emotions. That's not where it ends. You have to take into account what kind of dresses people are wearing, what is the color of the ambient, whatever objects are kept in your field of view. Everything has to be taken into account. So it's all a very sort of consolidated concept. So these are things which are also evolving a lot into in aesthetics, basically and only because light and objects have this very, very interesting interrelationship. I think that is something which you need to keep in mind. The colors are much more deeper than they appear. Okay, so let us move to Acha. So
Sir, I have a
ah,
question.
yeah, tell me.
Sir, it's not very clear how, like, why at resonance you have both absorptance and the reflectance maximized. Like, you can only maximize
No,
one of the
so
two things, right?
basically, yeah. So there are
Because the
two
total is
different things.
constant.
Sorry. What was constant?
Be- Because the total thing is constant, right? The reflection plus absorption plus
No.
transmittance.
Reflectivity. So
So how?
basically, you have to take into consideration something called the reflectivity, right? See, you are confusing two things. When I say absorption, so there is the absorption coefficient that is maximized. Whereas what I am talking about here is the absorptivity as given by the Fresnel relationships, which is a consequence of the absorption coefficients. So don't confuse that. Absorption coefficient does not mean absorption. Okay. So the
In
absorptivity,
this
reflectivity,
just
everything come as an interplay. What? Tell
but
me.
they're directly related, right? The
No,
coefficient
but they're
and the
related as per the Fresnel relations, right? See, they are related as per the Fresnel relations. Okay, the relationship of how the reflectivity works is not given just by the coefficient. It is the interplay of both coefficients. It is not just k alone, right? It is, in fact, you see, I mean, it is basically how much is incident by, I mean, it's basically the ratio of the two refractive indices. So what finally comes out is, so again, the reflectivity and the n and the k, they are not the same. This is the combination of n and k which give you the reflectivity. Okay, so it may be that the k is high, the absorption coefficient is high, but the net effect is not very high absorption. On at resonance, you still have very high reflectivity. Okay, so that is the concept. I mean, the reason. So essentially, what you can think of, what we will do now also, it is something to do with the electrons sort of, absorbing and re-emitting. So now think of it. Okay, I think a good way is this. A very okay, very nice. Good that you brought this up. So what do we think? In fact, I think there it will be here. It will be maximum understood. So if you just think of some kind of, so okay, let us just write down the expressions first. I'm immediately coming back to this. Just give me a second. So basically we had the two relationships. If I just write down, your n1 is equal to 1 plus e square by 2m epsilon naught. Acha, correct me if I'm wrong, huh? I tend to make bad mistakes here. Ni wi square minus w square by wi square minus w square. Was there a whole square here? There's a whole square here, right? Plus gamma I square omega square, right? And your n2 was e squared by 2m epsilon naught I ni gamma I omega divided by the same thing. is fine. Okay, this is absolutely fine. Okay, okay. So now, if we just think of the quantum mechanical analog, the quantum mechanical analog, in the sense that we kind of say how this will appear if you just consider, maybe electron levels. You want some kind of, two states, E1 and E2, and then you have, say, several levels. So, are you guys somewhat familiar with things called like fine structure and hyperfine structure? Have you heard these words? Have you heard these words?
Yes, sir. We had a advanced quantum mechanics course. Like
Yeah,
something.
advanced quantum mechanics में वो सुना था ना, right? So basically, electrons have, so it is just not the principal quantum number. There's a magnetic quantum number, the angular momentum quantum number, that is L, and then you have also the spin quantum number. So they sort of contribute, combine to give you L plus J, L plus S to give you J and all that. Suppose these are some principal quantum numbers, okay? Each of them. Now, each of them will have some kind of fine structures, okay, and then these will also have some kind of hyperfine structures, say, okay, things like this, like that, okay. And so what I mean here is that so my any two levels are basically maybe from something from here to here, some transition like this, some maybe I say that these are some hyperfine numbers, say 0 1 2 2 4 whatever, yeah. So, and this is say n equal to 1, and this is some, some S state and L state, which, okay, S and N will not give you this, but yeah, so I should make this higher actually. Yeah, but depends on the internal spin. So if the, so basically there are two things. Okay, so this breaking happens because of the spin of the electron. Okay, so this is essentially, this structure comes because of L plus S equal to J, and this structure comes because of I plus J, which is F, where I is the nuclear spin. Okay, so if you have a high enough nuclear spin, you have many levels possible, and this will go from minus F to plus F, it's possible. Okay, anyway, so what I'm trying to say is that we have transitions between, say, this 1 to 2, or sorry, this is 3, right? So 3 to 3, this is two sets of levels, and I have n I such things there. Okay, I such, transitions happening, things like that. So essentially what I mean is, in this case what I will have is something like omega I. This will nothing be the energy difference between my ground and excited states. Your basically this Ni that I have is something known as oscillator strength. So has somebody heard of this? Okay, maybe you have not. So oscillator strength essentially means the probability of transition between level I to J, and this gamma I is essentially the probability of transition to all other states. So what I'm trying to say is, this one is essentially the transition between, say, this state to that state, only these two, and this will basically sort of come, be dependent on how close this omega is to, this has a natural frequency, right? This natural frequency is nothing but omega 0. Okay, this guy, and omega is of course the frequency of the incident light. Okay, so then how far your actual light is, how far the incident light is actually detuned from this exact transition, so that kind of dictates what this oscillator strength will be. If it is exactly on resonance, we have a large oscillator strength, and if it is not, then it will be less. Okay, but what this one means, this gamma, is basically means it is like some kind of a broadening. So it means So there is, however, so while the selection rules basically say that you should only have transitions between this level to that level, there is still some probability of this one coupling to all these others. This is very small, but it is there. So this is like an overall damping factor. Okay, this is like an overall damping factor, and that kind of tells you. So the larger this is, the more. So your resonance essentially, if it is very small, then you have exactly a very sharp peak, like sorry, you have a extremely sharp sort of peak like that for small gamma, for the transition probability small gamma, and if it's a large gamma, you have a very sort of a spread out transition probability. uh, this large gamma. Okay, this is a large gamma. So essentially what I mean is, this is some kind of transition probability. Okay, so now if we just come back to what who was asking that question, was it Anurag? Anyways, that question of this absorptivity. So finally, remember the process that happens is the a sort of a re-emission. So the electrons absorb and then they re-emit. So what you can think of, if I want to justify, this thing of a reflection being large in case of high absorption, what you can say is that if my absorption is large, that means all the electrons are, or the electron is sort of getting very optimally transferred from this small state to this large state. Okay, and the final re-emission process, that is the reflectance. That is what actually you're seeing. So therefore, that is also very large. Okay, so therefore, the absorption and the reflectivity being high, those are not contradictory elements. If I'm actually absorbing very optimally, or I'm absorbing all the light that is incident, I will also re-emit very successfully, because remember, the electrons will not stay at the higher energy state. They have to come, all matter wants to come to the lowest possible energy state. So basically what I can
So
say here, huh, is high
how can we say
absorption
that?
also means high,
So
let
how
me
can
just
we say
write
that
this down.
re-emission is the same as reflection?
Some way you can, because finally it's a scattering process. Finally what we have is electrons. Yeah, who gives the light out? Finally it's the electrons, which, see, we are studying. I mean, the whole context of this refractive index, what we are studying is nothing but the electrons being bound to a nucleus, right? I'm actually going into a single electron level.
So, sir, we have not taken consider the case of fluorescence now till now, right?
Fluorescence also, yeah, that is, see, again, Priyanuj, that fluorescence is a completely quantum process.
Yeah. So we have
Fluorescence I
not considered
cannot
fluorescence, right?
absolutely compare with this. But then see, at the same time, when I see a certain color, that has to be like it is sort of some absorption and re-emission, because otherwise it doesn't. In fact, when we will just now do this phase velocity, group velocity thing, not group velocity, I mean, we are not assuming pulse of light. No, we'll be looking at phase velocity. There also you can say that finally what comes out is some kind of scattering process from the electrons. Okay, so that essentially means that I'm taking them to a higher state, and I mean, they're absorbing and re-emitting. You just think of, okay, let me just extend this. When we were discussing the Brewster angle, right, what were we saying? We were saying that the whole premise of the Brewster angle was that the electron cannot radiate in the direction of the reflected field, or re-emit, right? That is why for p-polarized light, incident p-polarized light, you don't have a reflected component, right? Because there also we were taking recourse to this electrons re-emitting, which would basically mean that the k vector of the light is in the same direction as the incident electric field, for the, I mean, k vector for the output field. And that again we were saying that the electron vibration direction is becoming the same as the k vector of the reflected field. Therefore, it cannot exist. So we do
But
take
sir,
recourse to single
in
electron
booster
levels.
angle, we have
Huh,
a particular angle at which that is not possible. But here we are
huh.
talking about reflection in general.
No,
So
no, no.
I
But I
don't.
also have resonance frequency. Please, I'm talking about this at the resonance frequency. I'm talking about this. So this reflectivity will be very high only when we are right on the resonance frequency. I mean, very close to the resonance frequency. I'm
Yeah,
not
that is
talking
fine.
about all possible things. So I'm
No,
saying, right? Yeah, Hitesh. Yeah, tell.
yeah, so I'm saying for like the analogy that you gave for the booster angle, that is
Huh?
only at a specific incidence angle. It
Right,
is not
right.
possible for. But here
Yes, but
we are
this one
talking about
also is for a
resonance
specific
frequency.
thing. Na? This is also I'm
It's
saying,
not dependent on any incident angle.
no, no, this is not dependent on any angle at all. This is basically coming. Oh, nah, nah. Then that okay, okay. Oh, that's a good point. Good point. See, now if I come with different kind of angles and all, that makes it much more complicated. Here I am only assuming normal incidence. Okay, if I assume the entire federal for formula, money, you have those cos phi's and all coming in. That makes it much more complicated because then you have to really solve, you have to write this n1 n minus ik and all, you have to put that angle and all, and that becomes complicated. Of course, that does not see remember, don't miss the context. What we are talking about is normal incidence with the wavelength of light being extremely close to the resonance frequency of the electrons in the sample. In that case, I am saying that reflectivity is very high. And I'm also saying that that does not contradict the fact that the electrons will absorb higher. That is, they are not
Here,
contradictory.
may I add a
Sir,
point
I
here?
just
Sure, Bishwajit. Yeah, Bishwajit may wants to add a point. Yeah, please come there.
Yes. So previously you said now that absorption coefficient is not related to absorption. No, I think you
Absorptivity.
mean to say absorptivity. I think you mean to say transmission coefficient is not related
Ha,
to
ha, ha. Yes, yes.
absorptivity. Because that
Ha.
transmission coefficient comes
Hmm,
from Fresnel equation, and then the whole point is fine because that a
hmm.
particular wavelength is absorbed and other wavelengths are transmitted. So
Ah,
then
that
the
also, yeah,
reaction
that way
occurs.
also is fine. Yes.
Yes.
Yes, but
So,
I think Bishwajit, the contradiction, I think for most of.
so then sir, there is no contradiction. I think you miss the term because you
Okay,
that
so that
absorption
way, that
coefficient and
what Bishwajit
transmission
is saying is
coefficient.
not bad. Yeah, what Bishwajit is saying also is not bad. What he's saying is that for the particular wavelength which has high absorptivity, I do not have any transmission. It is reflected off. It is reflected off, while the other wavelengths can either get transmitted or they can be absorbed. But then there
Yes,
is transmission is very low. That is also correct, but at the same time we tend to kind of we sort of we tend to associate absorption with bad reflection also. That is not true. Okay,
No, that
that
is
that
not
one
true
can
here also.
actually
No,
write. Huh.
you can
So
say that.
basically, high absorptivity may lead to poor transmittivity. That is certainly that holds strongly. But
sir,
reflectivity,
I only
hmm,
had a problem with the analogy of saying that reflection is similar to re-emission of light. So, because re-emission
hmm.
has no particular direction, right? Like a
That
photon
that
can be
is
re-emitted in any random direction.
No, but
that
yeah,
is another thing.
re-emission.
That is another thing which we
Like,
will just now
re-emission cannot be
come.
linked to
See,
reflection is my problem.
Anirudh. So that is another thing that we will come right now. In fact, a scattering process, one can actually show that when you have unidirected light, okay, typically what we assume is that scattering in all directions actually gets cancelled off except the incident direction because of interference effects, because of phase lag and all. Okay, except for the, so if you think of it, in fact, that is what we are going to just now come to when we are looking at this phase velocity greater than c, what it means physically. So we actually assume that when we are coming with some kind of incident light, then transmission actually happens, the maximum transmission happens in the direction of the incidence, because the scattered light in other directions, if you take the sum total, then the phase shifts act in such a way that most of the other directions get cancelled off. I mean, there's a probability of emission in all directions equal, that I completely accept. But what happens is finally you do not get transmission in re-emission in all possible directions. The maximum happens either in the direction of light or in the backward direction. Okay, so actually other directions get interferometrically cancelled. So that is not something very intuitive. In scattering of light, I'm not really going to cover this too much in the course, but I will maybe ask again, maybe when you do the term paper, I think somebody can pick this up and talk about this. But actually, you do not, the probability of scattering, I mean, it does appear that it's going to go in all directions, but actually what happens, because you can also sort of see that the maximum, uh, uh, yeah, I don't know whether we can, in terms of physics, we can just physically defend this, but so the phase, because there is a completely opposite phase lag between two angles separated by pi, what happens is the amplitude factors which are responsible for emission at other angles than 0 and pi, all of that sort of cancel out. You basically get only in the direction of, I mean, the transmission happens in the direction of incidence, or you can at times have on the backward direction also. That is different, but that's also very small. Okay. So, see, our basic argument here is saying that at high absorptivity, what you will basically get is also high reflectivity, and
Yeah, that is fine.
that actually is what we are trying to stress on. Okay, and it is all. Yeah, one thing one can stress is that the transmission is bad. That is clear. Okay, but the reflectance also is very large, and that I am trying to sort of defend in some way, in the sense that when I'm actually getting high reflect, I mean, so you can say that the re-emission that is going to happen is mostly in our, in the reflected direction. It's not so much in the direction of the incident light. So that I don't know whether there's a very nice, I mean, consistent theory coupling, the quantum understanding and the classical understanding here. But the classical coefficient tells you that the reflectivity is going to be very high, and also it is telling you that transmittivity is very, very less at the resonance wavelength. But uh, why exactly, in terms of physics, why the reflectivity will be very strong? Exactly justifying that is probably non-trivial. That I'm not sure that one can exactly justify. Okay, so yeah. So any more questions on this? So if not, let us just.
Sir, so if you have a monochromatic wave, in that case, if you have high absorptivity, you won't have high reflectivity as well, right?
You will have if you have a resonance wave, if you come at the wavelength where this is resonant with the material on which this is incident. If you come with a monochromatic wave at a wavelength on a material which is resonant at that wavelength, then the reflectivity will be quite high.
Okay.
Is that clear? If you have monochromatic light, which is of course at a different wavelength, then it will be partially transmitted, partially reflected, partially absorbed. Okay, so basically let me just write down that also. So for monochromatic incident light, reflectivity will be large if the wavelength is close to the resonance wavelength of the material. Is this part clear?
So that means there is very little actual absorption. Like mostly it is either transmitted or reflected. Like
No,
net
transmission is
absorption.
very less actually. Transmission will be less.
Yeah. No,
Absorption
like
basically,
yeah.
in the sense that the reflectivity basically gets quite large actually. That is
Yeah,
true.
I'm
Reflectivity gets
saying
large.
that if we look even at points which are off resonance,
Mhm.
then will the same thing hold? Like
That
the
we have to, okay, so one exercise that I will give you is to actually calculate the whole reflectivity spectrum of a material. So I think what you guys need to do is do a bit of research. I'm going to give that as an assignment. Basically, there is a material on which this n and k are all available from for a large gamut of wavelengths. Okay, so you plot the reflectivity and check. I can't. This is, it's not fair to just hypothesize on this. Okay, that is the assignment that's going to come next after we finish this part. Let's try to finish it. Maybe let me see if I can finish today, or else certainly let me see on Monday. So okay. So anyway, so let me just quickly write down. Let me just draw the thing that we had. So basically, the reflectivity, transmittivity characteristics were something like one was something like this, and here you had something like this, right? So this one was your omega, this is your k, and this one was n minus 1. So now very clearly you can see that, and this is of course your omega 0, this one. So very clearly you can see. Acha, so you know which level is which, in the sense we have three regimes, right? We have this and we have this. So in terms of dispersion মানে how n changes with omega. What would you I call these three regimes as? You understand what I'm saying, na? How n changes with omega. Typically, what is the understanding? That with increasing wavelength, what happens? What happens? Typically, the refractive index decreases or increases. Arey? What? So basically, I'm saying these three regimes. This is one regime, this is one regime, and this is another regime. This is another regime. So let me just write down. This is regime 1, this is regime 2, and this is regime 3. Maybe you should. You understand what I'm saying, right? So this omega 0 is here. This is the place where it's like between around this part. So this is your 1, this is your 2, this is your 3. Oh, that's not right. Yeah. So tell me, with wavelength, typically what happens to n? Are
increases from
huh?
that maximum minimum.
Increasing wavelength refractive index increases.
No, frequency, with increasing frequency.
Ah, that is what is expected, right? So as omega increases, n also increases, right? Correct? Right? So this is basically normal dispersion, right? And here, of course, your k is very less. It is almost close to zero, extreme, quite less. I have drawn this a bit wrong actually. This is quite very low. It's quite less. So this is the part that is really interesting, right? So here, as you have this increasing n decreases, right? This is not what is normal. This is actually anomalous dispersion, right? And your k is much greater than 0, right? Here again, however, this part, again you have the same kind of thing. Let me just write. Oh, okay. So this part again you have as your omega increases, n sort of increases, and it's back to sort of normal. Normal. However, it is also clear that your this n1 that n that is sort of less than 1. Okay, that is also somewhat clear. Okay, and at infinity, of course, at absolutely omega equal to infinity, again you get n minus 1 tending to 0, or n again tending to 1. So this is the interesting, very very interesting part, where you get all kinds of very very nice things happening. Okay, and that is what we are. So basically, before we go to things like, and what you can also understand is what's going to happen is, especially at like this part and all, when it's lower, you will actually get n minus 1 less than 0, which basically means that your phase velocity will become greater than light, right? Because it is it is c divided by n, and n less than 1 money, it is going to be more than this thing. So what does that translate to? What does that mean? Okay, so that is what we are maybe just have a look before we proceed to that, and to an understanding of that. Maybe we just sort of write down all the optical constants, the optical constants at different frequency regimes. Okay, so what about basically we are saying is, at omega less than omega 0, at and at omega greater omega 0. So here I'm not going to write down. I mean, I'll ask you to check these out. But what I'm going to probably just write down these values. You can just check these out. This is given by some omega p square omega 0 square, and your n is given by 1, and this is just n is going to be half of that. So these are very simple. You just go and check them in the formula. Just put the different values, you will easily get these. Okay, then this one is nothing but omega p square gamma omega by omega 04, and your k is same, omega p square gamma omega 0 to the power 4. So one thing that you can again very clearly see here is that as you go towards large omega, I mean small omega, this one. So yeah, very interesting. What are the takeaways? So takeaways.
There is a half factor in the case.
So takeaways is very interesting. This is almost constant, right? Is independent of your omega. This is almost constant. This is like a DC. Very very interesting, right? And epsilon r2 tends to 0 for omega, as for omega tending to 0. It's very very interesting, right? There's no loss. It's completely transparent. There is absolutely no absorptivity, right? And this one is this is more crucial when we will actually consider this the effect of like crystal oscillations, where we will so electrons, so in lattice vibrations, we take the vibrations of the electrons, just the electrons themselves, where they are not coupled to the lattice, and that is typically for the low frequency. We just assume this kind of constant behavior of the dielectric constant, and of course for high frequency we write down the entire expression. But that is very crucial, that that is almost like DC. For low frequencies this does not even change, right? Now if I write down for omega greater omega 0, we basically write your epsilon r1 as 1 minus omega p square gamma square plus omega square, which means your n is just omega p square by twice gamma square plus omega square, right? And this one is omega p square gamma by omega 0 square plus gamma square, and your k is just half that, 2 omega 0 square plus
Not omega 0, sir. Only omega.
sorry. Okay, it's just 2 omega 0 square gamma square plus omega square, right? Yeah. Okay. So very interestingly, what we have is that when you actually go for lower in that intermediate region, what you have is uh, that uh, you basically have this reflectivity very high. But what is very interesting is as you actually so near resonance, the phase velocity may exceeds that of light. So that is very, very interesting. So there we have actually a nice reason for this happening, which probably we are almost end of today's class. I don't. Yeah, this is probably not going to be a good idea. Okay. So by the way, so let us just end with this discussion. So I sort of did preempt this a bit, even in the last class, that what is the problem about this? I mean, is there a problem about this at all? In the sense, this phase velocity exceeding that of light? Yeah, guys? Do you think that it violates relativity?
But I
Sir,
don't
there is
understand
no
how it is
information
possible.
travel.
Yeah. So basically,
Information.
that's what we had also decided, that basically there is no kind of, so remember, so I'll just write that down. This, however, does not violate STR since no signals can proceed, can still proceed at velocities greater than c. So I will, yeah, maybe I will just stop today. What we will do is next class we will basically try to figure out the, the physical reason as to what is actually happening, and then because we maybe, but still, I think one can. No, yeah, okay. So yeah, I will give the next assignment probably on the next day. That is at on the Monday. I think we will just end this part and then we go on to the Drude model. And let me stop presenting. Yeah. So any observations about today's discussion? I think we had a good discussion about these colors and absorption and all that. You want anything to discuss on that or what? So by the way,
Go clean,
tomorrow,
sir.
so tomorrow, if there is a tutorial, then you guys please set a time and use the same meeting link. 5 o'clock, I think we decided, right?
Yes.
So, any more questions on this? Any observations? Anything? By the way, has
This
anybody
party,
looked at that great thing that we had on this critical this thing? What was that? Your non unpolarized light reflectivity. Anybody took any steps towards looking at it? Nobody. अरे क्या यार? Huh? Anybody thought of doing this? Checking it out? Nothing. Huh? I thought it was a fun experiment. No, about what? Too many classes happening. Okay, sad. So yeah, because I really find it. I think it's quite intriguing. I mean, what is going to happen at different angles? I feel there's going to be a dependence, but the theory is not that easy. Hmm. Anyway, I really feel that once you guys get some time, just try to set up some stuff. Very simple. It will probably take you an hour or two. You are getting bored, with lockdowns and all. Just try to take a bulb, put a pinhole, get some collimated light, take some piece of glass wherever you have, break a glass or something when nobody is looking, a drinking glass or something. Break it. Somebody is not looking. Take try to without cutting your hand and all that, of course. And just take a camera and do some. When you use your hands, yeah, get your hands dirty. That's how you will learn physics. Okay, okay. So we will meet again.
this part is done from Bohren-Hoffman, no, sir?
This part is mostly covered. I will give the reference the next class. Mostly it's Bohren and Hoffman. Okay. Okay. Then let me stop recording and let us meet next Monday.